due to a charge distribution is given as, if there is a charge distribution at r prime and I am calculating potential at vector r, then the electrostatic potential V r is given as 1 over 4 pi epsilon 0 integration rho r prime over r minus r prime dV prime, where dV prime indicates that I am integrating over the r prime variable or over this volume where the charge distribution is non-zero. What we will do in this lecture is use this to calculate potentials for a 2 or 3 charge distributions. The examples I am going to take are going to be: 1, a linear charge of charge density lambda per unit length, a ring of charge of radius r, again carrying charge lambda per unit length. This can be easily generalized to a disk of charge, which we did earlier in the case of electric field, or force on a charge q, but I am going to use it this time to calculate the potential due to a uniformly charged shell, a spherical shell carrying sigma charge per unit area. So, let us begin with the line charge, and let us say this is given at the origin with the center at the origin. The length is from minus L by 2 to L by 2, and now you see the advantage of using potential to calculate electric field later, because in the potential I do not have to worry about any components. All I have to do is, if I calculate the potential due to this small charge lambda dy, then all I have to do is calculate lambda dy over 4 pi epsilon 0, and the distance of that point from r is going to be r minus y unit vector, and just integrate, and y varying from minus L by 2 to L by 2. No components, nothing, just one calculation. So, let us just do that. So, this is going to be integral. So, this is V at r, or I can write this as V x, y and z is equal to lambda over 4 pi epsilon 0 comes out, and I have minus L by 2 to L by 2. The charge is sitting on the y axis, x, y. So, x and z components of the charges are 0, and therefore, I have dy over square root of x square plus z square plus, I am calculating it at some point y. So, I should just change the notation a bit. I will put a prime to indicate, as I have been doing, to show that it is a y prime over which I am integrating. So, I am calculating field the potential at y minus y prime square. That is it. That is the integral that we are going to do. Let us now, to do the integral, let us take x square plus z square to be some rho square. So, V x y z is given as lambda over 4 pi epsilon 0 integration dy prime over square root of rho square plus y minus y prime square. Y prime varies from minus L by 2 to L by 2. To perform the integral, let me write y minus y prime equals rho tangent of theta, so that I have minus dy prime equals rho secant square theta d theta, and the limits are from theta 1 equals tan inverse y plus L by 2 over rho to theta 2 equals tan inverse y minus L by 2 over rho. So, that the integral now can be written as V x y z equals lambda over 4 pi epsilon 0. This minus sign changes the limits the other way. So, I am going to have theta 2 to theta 1 rho secant square theta d theta over rho secant theta, and this rho cancels and one of the secant thetas cancels, and I am left with a secant theta here, and therefore, the potential then becomes V x y z equals lambda over 4 pi epsilon 0 theta 2 to theta 1 secant theta d theta, which is nothing but lambda over 4 pi epsilon 0 log of secant theta 1 plus tan theta 1 divided by secant theta 2 plus tangent of theta 2. That is the answer. Now, of particular interest is either you take limit L going to infinity or y going to 0. Let us take the limit L going to infinity. In that case, theta 1, which was equal to tan inverse y plus L by 2 over rho, becomes tan theta 1 equals y plus L by 2 over rho, and tan theta 2 becomes y minus L by 2 over rho. This gives V x y z as lambda over 4 pi epsilon 0 log secant theta 1 plus tan theta 1 over secant theta 2 plus tan theta 2 equal to lambda over 4 pi epsilon 0 log of secant theta 1 will be 1 over cosine theta 1, which becomes 1 over, let us check that, tangent of theta 1 is y plus L by 2 over rho. So, this will become rho over the square root of L by 2 square plus rho square plus y plus L by 2 whole square. Oh, sorry. We have tangent theta 1 is equal to y plus L by 2 over rho, tangent of theta 2 equals y minus L by 2 over rho, and therefore, secant theta 1 is equal to square root of rho square plus y plus L over 2 square divided by rho, tangent theta 2 is equal to square root of rho square plus y minus L by 2 square over rho, sorry, this is secant theta 2. You work all this out and in the limit of L tending to infinity, so that L plus or minus L by 2 plus or minus y can be taken as L by 2, you get V x y z as equal to lambda over 4 pi epsilon 0 log of 4 L square over rho square plus 1. 4 is not on top, 4 is on the bottom. It comes out to be this, which I can write as equals, since L is much greater than 1, L square over 4 rho square is going to be much greater than 1. So, I can write all that as V x y z equals lambda over 4 pi epsilon 0 log L square by 4 minus log rho square. As L tends to infinity, this fellow goes to infinity. However, in calculating potential, I can always neglect that infinity part. So, I can write this as lambda over 4 pi epsilon 0 minus times minus 2 log rho, which is minus lambda over 2 pi epsilon 0 log rho. That is the answer for L tending to infinity. This matches well with the conventional expression that you know for an infinitely long wire.